Okay, should be recording now. She sent me the key version, so I'm not entirely sure what parts she has already given you. It looks like she gives you already the resistance, which makes sense, and the battery. She says that the battery is 12 volts. That resistor A, I'll write it in here. Is 5 ohms. I don't have the ohm on my keyboard, so I'm just gonna put 5, and you know that it's ohms. Resistor B is 2. It is 3. So from here, we can go ahead and try to start adding everything. We know that we're gonna have to collapse this B, C, and D all together. But they do have this little S1s up here and S2s. I don't know if that's just part of the problem because it looks like she solved it regularly. Because those are just switches. So I would assume that the switches are closed. So I would assume that the switches are closed. It's because she solved it like that. If she says that the switches are open, then you're basically just gonna ignore those lines. So you would only do A and C. But she seems to want your I and B for all of them. So I would assume the switches are closed because that's the only way you can be able to calculate them. So anyway, we have changed color. We have B, B, C, and D, which are in parallel.
Oh, Andrea's in the waiting room.
Okay. There we go. Thank you. They're in parallel. So how are they going to be added? Is it going to be the 1 over or the added straight? Okay. Because it's resistors, it's going to be added as a fraction. Something that I used to like to draw like on the top of my little exams. I would just memorize it and then write it down. So resistors. Oh my gosh. I'm just gonna put R for resistors. In series versus in parallel. Sorry, I'm using the computer, so it's a bit harder to do. Then have same. In series, they're gonna have the same current, but different voltage. And you're gonna add them regularly. But in parallel, they're gonna have the same voltage, different current, and you're adding them as fractions. So I will just use this as a reference because I used to keep it on the top of my homeworks or whatever, just to reference it. That means in this case, let me see if I can type this. E. And those are each over 1. Then you do your B, C, and D. And if we go ahead and add those, we get B is 2. B is 4. And D is 3. And then I'll go ahead and put the units in right now. Now, you could like fly them out to make sure they have a common denominator and do all that jazz. I would just use your calculator, quite honestly. Go ahead and plug that in. This. My calculator gave me 0. Calculator gave me 1.08. But then you have to remember that because you're adding in fraction version, your unit is 1 over ohm. So you have to do the inverse. It's 0.12 ohm. Okay, and that's the same thing as knowing that it's your number equal to your 1 over R total. So then you're gonna get your total equals 1 over your number. And that's just all the inverses, is 1 over it. So then you've got that one, and then you can add for all of them together. So here are total, because your RA and RBCD are going to be in series. I wonder if I can, oh, I can, nice. Because then what that gives you is your A. And then imagine it continues for the rest of the circuit. This is your A, and this is your BCD. So those are in series. And you can R here, RA, no big space, plus here RBCD. That's gonna get you. Our A is 5 ohms plus our 0.92 ohms. It's gonna be 5.092. So then that gives us our resistance for all of our components and our total resistance. From there, we can try and calculate our probably voltage. Or maybe, no, we have our voltage from the battery, so we would be calculating our current. So remember this equation, V equals IR. Can we arrange V equals IR to isolate for I? So I is equal to V over R. Right? We have our total voltage and our current total resistance. So we're gonna find out our current, our total current equals. So then we're gonna get our 12 volts from the battery divided by our 5.092 ohms that we just calculated.
Wait, why is it 092?
It's 0.92 because we just that's not what I meant. We just found it right here. So
But wouldn't it be 5.92?
yeah, sorry, 5.092. I wrote it right. It's right here.
Because in the, what's it called? In the other one, we put for the inverse
Mm-hmm.
right here. It
Yeah.
says 0 or 0.92. And then if we add those
Oh, I
five,
see what you mean. I think
yeah.
you're right. I added a 0 somewhere. Probably right here. You're right. See if I can edit this. No, you're right. I added a 0. There we go. Good catch. Anyway, we go ahead and divide that. And we get 5.92. I got 2.027, so we're gonna round it up to 3. And that should be amperes. Yeah. It's current, so it should be amperes. I usually try and figure out the units, but I feel like we could probably just trust it. If you guys want me to go through the units and how volts over ohms turns into amperes, we can do that. But it's just knowing what the volts and the amperes and ohms mean. Anyway, we can go ahead and continue. You know, this is our I total, and we know that this are resistors. Right now we're looking at the A and BCD, which are in series. Because they're in series, they have the same current. So that means that this total current is also equal to the current of A and the current of BCD. Which means we can go ahead and put in our current for A into our table. It was 2.03. And then we can use our current to find the voltage of our series, our resistors in parallel. So because they're in parallel, they have the same voltage but different current, but this is just for all of them. So we can go ahead and find the V. There. Our V equals IR. V. I wonder if I can. You guys know that if I put BCD, it's just me describing what that voltage is, right? It's not like multipliers or anything. You pick your silence as a yes. And it's multiplied by our resistance of BCD. Good thing is we have both our current from what we just found. That's our 2.03 ampere. Oh, I have chat. Oh, yeah. And then we have our resistance for BCD that we found up here. That's the 0.92. I just leave space drawn in them. And that's gonna go ahead and get us 0.03 times. I got 1.8676, and because it's ampere, it should just be volts, which that rounds up to, we'll say 1.9 or 1.87. We'll go 1.9. Cool. You can also calculate I'm gonna do it above because it just keep the A resistor together. You can also calculate the voltage of A. Because we have all of those components as well. So it's gonna be, A was 5 ohms. This one's the same, 3 ampere. And that's gonna get us 10.15 volts. And we can go ahead and write that up here as well. 10.15. I guess that'll be 10.2. Just so we can round it. And then we found our voltage for resistor BCD. And because we know that those are in series, sorry, parallel, they have the same voltage. So we can just plug that in for all BC and D. So that was 1.9. And then using those, we can calculate the current running through the individual resistors. Okay, I see that our session is gonna end soon. So we'll just finish calculating the current for these, and then you can come back on the same link after it closes. Anyway, 524. From there, we're just solving for I at this point. So we're gonna be using this equation. But for all of these. So. They all have the same voltage, so 1.9. But they had different resistance. For B, it was 2, and then C was 4. So it's 2, 4, 3. Yeah. For all of those. And then it was B, C, and D. And you can go ahead and put those in. Seven amperes. .6 amperes. And 2.8 amperes. Right, and then we can go ahead and put these into the table. Let's type in here. 8, 6. And then with that, you filled out your table, which was what that question was asking for. I'm gonna go ahead and stop the recording, and then we'll meet back on the next Zoom link.